All right, this is our final project for Intro to Computational Design and Analysis for Professor Malik. It's going to be done by Alejandro Hernandez, Kane Bobbier, and then myself, Luis Hernandez. So what exactly are we analyzing? We're going to be analyzing a tie rod for a competition style go-kart. What exactly does a tie rod do? So what a tie rod does is it transmits motion from steering here. You see steering rod here. So what this does is it rotates and it causes these tie rods, we have two of them, to rotate in motion, which causes these wheels to turn left and right. What exactly are we doing? So the competition style go-karts like tie rods that are optimized to their full potential and have excessive material. So what we're gonna do is try to reduce that material because weight is a big aspect in racing profession, and getting rid of every possible ounce of weight is crucial to its performance. So our design optimization is gonna be to overall uh, reduce the volume of the tie rod for our go-kart. We want to design the structure in a way to where less material is going to be used and still retain the similar mechanical properties. Um, our volume cannot exceed more than 1.32 cubic inches, and the aspect ratio of diameter to height must be 1 to 3 respectively. Um, so we're gonna do work with steel, mainly because steel is uh, the main type of material used in tie rods. We used a Young's modulus of 200 e to the 9 uh, gigapascals and a ratio of 0.3. We're going to do a uniform pressure load on the end of the rod of 33 newtons with one end of the rod fixed. And for our design variables, we're going to try and find the smallest possible volume of the tie rod. We have to import our initial rod diameter and length by placing them in the optimizer along with our constraints. And then we'll have an idea on the best dimension tie rod we can use. Alejandro's going to talk a little bit of the component details. Alright, so this is basically the first engineering drawing for our tie rod, and it basically consists of three parts. We have the ball joint, the locking nut, and the threaded rod. So for this drawing, this is our ball joint, this is our front view, this is our side view, and the material we're going to be using for this is going to be steel. This is going to be our locking nut. This is also going to be made out of steel, and it is going to be 0.5 by 0.33. And I made a little note on the side. This is going to be 5/16 by 24 thread. So this is going to be the main part we're going to be analyzing, which is our threaded rod. And this is going to be 6 inches with a diameter of 0.58. And this is also going to be steel. Okay, so what we found after analyzing our part on Abacus is that when we applied a uniform load of 33 newtons, this was the maximum load that this tie rod could take before failing. And we found that if we increased that by 1 newton to 34, uh, our whole tie rod would fail. It would go into compression, as you can see here. And these three figures, so in figure 1, this is basically the undeformed shape. Uh, this is the shape of the tie rod before the load is applied. And in figure 2, this is the tie rod when it begins to deform due to the applied load on the end. And then finally in figure 3, this is where the tie rod experiences the load on the ends right here, as you can see.
So this was the MATLAB code that we used for our project. For our initial dimensions, we used 0.58 inches as the diameter and 6 inches as the length. And you could see our upper and lower bounds. We didn't want to make the rod too long or too thin because of the common dimensions of a go-kart. We didn't want to stray too far from that. So these are our dimensions before and after optimization. As you can see, the diameter went down about zero point 0.1 inches while the length went up by almost an inch. So these are the results that we got after putting our new tie rod in to Abacus. And overall, we noticed that the von Mises stress went up incrementally. But we believe that's normal because the area is reduced. This is the process for our second tie rod. So the benefits of improved design. Competition style go-karts rely heavily on weight and strength, and we believe that finding the optimal volume would decrease the weight but not make the part too weak. So for our results, we were able to reduce the volume, and in turn we were able to reduce the weight of our tie rod from 0.36 ounces to zero point 0.3 ounces. And also when we put our tie rod in finite element analysis, uh, the new tie rod was able to withstand the same load without failure after decreasing our initial volume. Overall, we were successful because we shed a little bit of weight from the tie rod. So finally, some things that we would change. We wanted to perform more simulations um, with materials such as aluminum. We kind of wanted to play around with different material properties and see how that would affect the finite element analysis. Also, we wanted to see how our new dimensions would affect the price of the tie rod. And finally, we wanted to play around with different constraints to see if we could get different results. And these are some of the reference that we used.